Hello, everyone. I'm Kafma Hamza, a student of Makerere University. I'm going to briefly be talking about a brief overview of hu- holistic evaluation of language models, and I'll be taking you through the targeted evaluations in that particular research paper and the models that were used in this research paper. So the targeted evaluations, I would briefly discuss them as the focused assessments that address specific aspects of language models relevant to different stakeholders. Those are the researchers, the policymakers, and the general public. This evaluation also considers potential harms, focusing on disinformation and copyright issues, which are critical when malicious actors use models. So the targeted evaluations, we have 7 of them. We have the language, the knowledge, the reasoning, the memorization and copyright, disinformation, bias, and toxicity. So I'll talk about the first one, which is language. So language, as we know, the language itself, English, Chinese, we have different languages. So we're supposed to evaluate our model's understanding of, here in particular, this uh, in this research paper, they evaluated the model's understanding of English language using two primary methods, which was language modeling and minimal pairs. Whereby language modeling involves assigning a probability to each token, okay, each word in a text sequence, summing these to determine the probability of a full sequence of a full sentence, like how often a word is going to be interpreted in that particular language. Then minimal pairs, it involves pairs of sequences differing by a single token. A token is a number which is assigned to a word, where in language processing, that token is given to a particular word, so that if it appears again, the language model can identify that this is this particular word using the number that was assigned to it. That's a token. So minimal pairs involves pairs of sequences defined by a single token, where one is acceptable and the other is not. So we have this particular token, which is one, but then one of the words that it's associated with is accepted and the other is not. Then we have the datasets and selection, and the datasets we used for language evaluation. We used Wikitext, which comprises of verified English Wikipedia articles, the PILE, the Twitter AEE, a corpus of over 50 million tweets, ICE, the International Corpus of English, a set of corpus for analysis of 12 varieties of English, whereby there is Canada English, Jamaica English, Kenya English, Hong Kong, India, Ireland, Singapore, Philippines, Tanzania, and the USA. These datasets were chosen in particular to cover different domains and varieties of English. And by including them, we aim to evaluate model performance across diverse English varieties. I'll move on to the next, which is knowledge. Knowledge refers to the information and facts that a model has encoded and can accurately recall or use. These are the things that are stored in the model database, and like they can be retrieved by the model to be used to give information and facts. So to evaluate a model's knowledge, we used also two primary methods, where there was question answering and text completion. And the first one of knowledge-intensive question answering, we assess how well the language model can answer questions that require significant knowledge, including understanding the question, reasoning, and retrieving the correct information. So the datasets we used HELM and OpenBook QA. These datasets test the model's general common sense knowledge, which involves everyday information and logical reasoning. Then there is Truthful QA. This dataset emphasizes the accuracy and truthfulness of the model's knowledge. ensuring it can differentiate between true and false information. Then there is AMLU, which tests the model's specialized knowledge across a wide range of domains from the humanities and sciences to STEM, which are science, technology, engineering, and math. And then the other method uh, of evaluating knowledge, we have fact completion. This method isolates specific factual knowledge by using simple prompts to test minimizing the need for language understanding and reasoning capabilities. Yeah, so these facts, what we mean by these facts are the single facts. A prompt is a question we're asking this particular model, and then how well it's going to give us a particular fact. For example, I could give the example of how the capital of France is Paris. So I'm supposed to ask this particular model to give me the capital of France, and how well or good it gives me that fact, but that answer that it's Paris that's a good evaluation. And if it's doing that correctly, then that's a good model. I could give another question, pause for it, another question. Who is the president of Uganda? And it's supposed to give me the president of Uganda, and that's supposed to be Kaguta Museveni. So the data sets we used inspiration. The fact completion task is inspired by the Llama probe dataset, which established a method of probing models' knowledge through fact completion prompts. Then there is diversity, spans across 12 domains, including humanities, social sciences, the STEM fields, as we saw before. Then there is prompt templates. Then in prompt templates, each domain has 2 to 7 Wikidata relationships, which are identified, and the templates were created to convert the triples into natural language completion tasks. Then there is another one called benchmark creation. I'll move on to the third evaluation metric, which is reasoning. A targeted evaluation, sorry, not an evaluation metric. Reasoning refers to the model's ability to process information and draw conclusions based on given data or scenarios. To evaluate a model's reasoning capabilities, two approaches were used in this particular research paper, whereby the synthetic reasoning tasks and realistic reasoning tasks. So the reasoning primitives, which are the synthetic, there is non-ampliative reasoning, recursive hierarchy, and state tracking. So in non-ampliative reasoning, it involves drawing conclusions already present in the premises. So these conclusions are based on what we have. But then in ampliative reasoning, we draw conclusions that require more assumptions. And the data set we used for non-ampliative reasoning was implemented scenarios with abstract symbols for natural language deduction, whereas for ampliative reasoning, we used rule induct and numeracy prediction tasks. We move on to another reasoning primitive, which is recursive hierarchy, whereby the task involves generating the correct sequence of closing brackets. And we used the dataset of generalized Dick languages for nested structures. We have state tracking, where we use the Barbie dataset, which includes tasks like transitive inference, coreference resolution, and logical reasoning within short stories. We have short stories, and they give you a particular short story. This is mainly used in the medicine type of whereby a model is given a lot of context, whereby some is not useful and the other is not is useful. But it's supposed to draw conclusions, like maybe the person is given the signs and symptoms. The model is given the signs and symptoms, and it has to reason disease, carry out a deduction and get to know, not exactly know, but try to get to know what diseases it's supposed to move towards to. Then we move on to the other method, which is realistic reasoning, whereby there is mathematical reasoning. This is solving math problems, and we used GSM 8K and math datasets. Then we have code synthesis, which involves writing code to solve programming problems of varying difficulty. As most of us in our generation, we've used ChatGPT to generate code and maybe correct code. And the data set they used in this particular research paper, they used human eval and apps, which covers a range of difficulties in coding. Then there is legal reasoning. The model must identify which legal case best supports a given argument. They used legal support task as the dataset, which involves comparative legal entailment from actual legal opinions. There is logical reasoning, where a verbal constraint satisfaction problem is requiring logical analysis. So they used the law school admission test analytical reasoning questions, which are verbal versions of problems. Then there is structured data reasoning. They evaluate tasks like entity matching, determine if two data rows refer to the same entity, and data imputation, whereby we're going to probably have work, but then we have missing values. We're supposed to imputate this work and remove or fill in those missing values. Here they used restaurant and buy datasets. The fourth targeted evaluation was memorization and copyright. So language models have been found to memorize and reproduce content from their training datasets, which poses potential legal risks related to intellectual property and copyright. So if a model is able to acquire knowledge and reason from it, it's going to actually memorize some of these things, and it's going to keep on reproducing them when it's prompted to give an answer. But then in doing so, some of this work is copyrighted, whereby it's not allowed to go to some certain, not to be given to certain individuals or the public. So this is also supposed to be a targeted evaluation. Our models are not supposed to adhere to the community laws talking about copyright. So this process includes using 3 data sets, whereby they use the books corpus, the bestseller books, and Linux kernel source code. So here they've used books because books are the easiest copyrighted material we could get. And for someone to use probably text from a book, which is copyrighted, and the person gets, maybe the model provides this prompt to cause copyright issues. So prompts are formed by sampling varying numbers of lines from the beginning of this text from this particular data sets we used. Then the evaluation metrics to measure memorization and copyright. We used exact regurgitation, whereby longest common sequence normalized by the prefix length, and then the near exact production. Longest common, we see what particular words are running in common with the copyrighted work, and then how exact is the words and phrasing to the copyrighted work, to the original work. And yeah, so we went to conclusions that larger models and those trained on source code were more likely to generate content, which is exactly reused as it's stored in the source. Because you see, for code, there is some way code almost always looks the same. It's it's very hard to find change in code whereby there is a major change. It always looks the same. It's always the same way on how code is written. The only thing that changes is the way the way in which language the code is written in. But the same way all algorithms to solve a problem are always the same, which are used to write the code. So it shows that these larger models, which are trained on source code, are more likely to generate the same kind of code. So I talk about the fifth uh, uh, targeted evaluation, which is disinformation. So this information involves deliberately spreading false information to deceive or influence people. This often leads to significant social harms, such as disrupting democratic processes, undermining public health, and inciting violence. So effective disinformation relies on convincing content and strategic network behavior to propagate through social media and other platforms. So checking language models for disinformation is very crucial to mitigate the risks associated with misuse, protect public discourse, and maintain the integrity of information in society. So language models can easily create false information, keeping the security of the working in-house and the effectiveness of working remotely. However, they can produce a lot of text quickly, which can be made even better by human editors. But however, if a lot of editing by humans is needed, it can reduce these benefits. So the datasets we used, they used the misinformation reaction frames dataset on COVID-19 and climate change, which clusters headlines and creates supporting thesis statements. Then they also used a dataset called waging. The sixth targeted evaluation was bias. So bias in relation to language models refers to the systematic and unfair discrimination or favoritism towards certain groups, attributes, or characteristics encoded within the model. This has already been seen as an evaluation metric for the language models that are being benchmarked, because bias in language models is measured to understand and mitigate potential harms that these models might cause. It also comes back as a targeted evaluation because it focuses on evaluating both intrinsic biases within the models and biases manifested in their outputs during world use, the practical uses. So here we evaluate bias in two ways: in intrinsic as an intrinsic bias, whereby we assess the bias built in a model structure regardless of the specific task, and the extrinsic bias, which evaluates bias in the model's behavior when applied to practical tasks in the human world. So they use the barbecue dataset for bias evaluation. The barbecue dataset assesses biases in a question answering context, covering 9 demographic categories, which are age, disability, gender, nationality, physical appearance, race, religion, socioeconomic status, and sexual orientation. This takes us to the last targeted evaluation, which is toxicity. Toxicity in relation to a language model refers to the generation or amplification of harmful, offensive, or abusive language by these models. Now, this evaluation shows low incidence of toxicity in practical use cases suggesting a lower risk of harm from deployed language models. Models have been shown, models have been observed to generate toxic text when prompted, even with text which ain't even toxic. For example, reflecting social biases, whereby uh, there is associating Islam with violence, there is saying vulgar language, and it depends on the community you're in. Some communities take vulgar language to be normal, whereas some other communities take some vulgar languages to be okay. So the data sets used for evaluation is real toxicity prompts developed by Gehman. Chooses prompts from open web text stratified by toxicity levels measured with Perspective API. And then Bold, which provides a context to real toxicity prompts by evaluating the model's generation in more context. Uh, Thank you very much. I'll be back to take you through the models that were actually benchmarked. Hello, I'm back to take you through the models. As you can see here, this is a table showing all the models that were used in our in the benchmarking of that were benchmarked during the in the research paper. So the first column right here shows the model name, which shows the name of the language model along with its version. Then the second column right here shows the model creator and the organization or team that created the model. Then modality is the type of data the model processes, which is typically text, but we can see down here Code Da Vinci and Code Cashman. The modality is code, so they provide us with code. The hashtag parameters, the fourth column, the fourth column takes shows us the number of parameters in billions uh, in the model, indicating its size and complexity. Then the tokenizer is used by the model for processing input text. As I already talked about before, a token is probably in simple language is a number that is assigned to a particular word. So a tokenizer is the framework or the architecture that is going to be used to assign numbers to those words. Then the window size is the maximum number of tokens the model can process in a single instance. Then access is the availability of the model, either open, limited, or closed. So as we see, some of these models, they have limited access, whereby there is some limitation of the work or the things you can do with the dataset, and everything is not given to you. Then closed, this particular model you see here, it stays closed because it's not open to the general public, but it was only provided to the researchers of this research paper because they were carrying out this research. And then the open ones are the models that are actually open to for public use. And then we move on to the total tokens. The total tokens are the total number of tokens the model was trained on during the training process. The total queries are the total number of queries or uses made to the model. And then the total cost, the cost associated with using the model, often or it's measured either in money or GPU hours, how much hardware was used. So this takes us to what I've been trying to tell you before, that there were actually 30 models that were benchmarked. Some models were open, some were limited, and others were closed but accessible for this research. And then issues such as missing models, live system updates, and isolated technical problems were noted. And then model contamination and fairness in evaluation was addressed, emphasizing the need for more transparency and standardization in future evaluations. This takes us to the process of the experiments and using the metrics we one of my colleagues talked about, and things like toxicity, accuracy, and bias, whereby these particular models were benchmarked using those particular evaluation metrics. So to see how good and how bad they were in providing us with the context, which is how the targeted evaluations we've been talking about, how biased they are, how the language is evaluated. Yeah, and this brings the conclusion to my presentation. Thank you for watching.